In this video, I'm going to give a walk-around tour of my latest home-built recumbent. I'll limit the talk to its features and some of the thinking behind the bed rather than discuss the minutiae of construction. Before I start the walk-around, I'll give some of the history that led to the bike I'm riding today. In 1997, I built an aluminium prototype with hacksaw, drill and file to help me decide whether I should continue down the recumbent rabbit hole. It served me well for years, but with no suspension it gave a bone-jarring ride. By 2004, I decided to go next level and build a carbon fibre short wheelbase bike with full suspension. I call this one version 2. The aim of the bike was to provide personal transport and had to be capable of commuting, shopping, touring, and most importantly, it had to be a joy to ride. To achieve that aim, I set my goals for the bike to be capable of negotiating Sydney's streets and cycling infrastructure, carry at least 15 plus kilos, and be of carbon fibre composite construction to enable complex shapes. Version 2 was designed exclusively with pencil and paper and the help of wooden mock-ups. Front suspension had simple sprung forks and the rear swing arm had an elastomer spring. V-brakes were on front and back. The seat angle was consistent with what I considered to be comfortable with urban riding. It initially sported a pannier rack to carry loads, but I added a tailbox. The foam came from Metro Foam in Silverwater. Common specs with version 3 are a 1.2 metre wheelbase, tyres are 451 by 28 at the front and 700 by 28 at the back. Hybrid style gearing with 26, 38, 48 chainrings and an 1132 cassette. Version 2 was satisfying to build and a fantastic ride, but there were some things that could have been improved on. So by 2014, I decided to go the whole hog and commit to version 3, sporting better airshock suspension and a higher bottom bracket that eliminated heel interference, plus a more comfortable seat and more integrated controls. Knowing the mental gymnastics I went through designing the compound curves of version 2, I decided to try CAD modelling. I chose SketchUp, which did the job, but being oriented to architecture was not a good match to my needs. So let's take a look at version 3. Starting with the frame, it has a slacker seat angle and a higher bottom bracket. It's modular in design, so components can be easily changed. The frame's aluminium hardpoint, precision jigs and mandrels for winding parts were made for me by Jens Frey from Heartland Enterprises at Monavale. The frame started with a foam core, internal cable, wiring guides and component mounting tubes, and then mounted on a jig and then wrapped in carbon fibre. The frame has a 20 centimetre extension on the rear that the tailbox mounts onto. Next is a fork, and that was made for me by Wayne Kotzer from Gundaroo. He mated a Cannondale head shock with a 20-inch chrome moly fork. Here is a valve extension for pressurising the fork. Wayne also made the aluminium head tube, bottom bracket and some fixtures. Here is an early version of the head shock with a plain spring and short stroke. I went for disc brakes on the front because of the experience I had with rim brakes on version 2. My local Concord bike shop made me some wheels from Alex Rims type DA22. They might be considered heavy, but they're robust enough to withstand the rigours of my daily commute. So onto the rear swing arm, a cantilever style design, typical of what can be seen on some folding bikes and mountain bikes. This design provides easy access to the chain and wheel, plus I think it looks nicer on this style of frame. I tried to locate the chain line close to the pivot axis to minimise pogo and kickback effects. Suspension for the swing arm is provided by a RockShox Monarch, which features an adjustable damping and a lockout lever. While we're here, observe that the rear derailleur is a SRAM mountain bike type. At the time of design, it was the only one I could find with forward-facing cable entry, which allowed for a standard length cable. Short arm V-brakes help clear the tailbox at the extreme of swing arm movement. Despite the smaller mechanical advantage, you don't have to try too hard to lock up the back wheel when braking. The coated aluminium pivot and polymer bushings are made by IGUS, a manufacturer of machine and robotic components. IGUS is sold by Triatham Automation in Brookvale. The bushers press into the swing arm with an interference fit. The swing arm is held in place by the pivot that is pressed into the frame. A retaining plug stops the bushers from coming adrift because I made their housings a fraction too loose. The big advantage is they don't require lubrication and therefore don't attract dirt and don't care about water either. And so far, they seem to be extremely long wearing. I went for polymer bushings because version 2's steel pivots and bronze bushers had corrosion issues in wet conditions. Let's move on to the chain. A higher bottom bracket enables an almost straight line on the drive side. The idler pulleys are made and supplied by MR Recumbents in Victoria. A guard in front of the seat prevents cyclist tattoo. The seat is a spoon type design retained by 4 M5 bolts into the frame. You can see 2 covered bolts there. The frame has threaded plates with mounting holes 10mm apart for fine tuning of the seat position. In normal use, the seat operates in compression against the frame, resulting in very little stress on the fasteners. Peter Hill made the seat cushion and it's very comfy, thank you. What I call the steerer is a tube structure that cantilevers from the head tube part of the head shock and can be considered a head stem taken to extreme lengths. The first steerer on this bike was articulated because I thought the slacker seat angle would make getting on and off more difficult. I found out over time, however, that I could get on and off easily without tilting the steerer, and that freed me to design something that made access and maintenance easier. Incorporated into the steerer tube is a suspension lockout lever. Suspension working, suspension locked. The battery, control cables and wiring are mounted to the front of the steerer and are protected by a clip-on fairing. The two-part console houses the LED headlamp, lighting controller, electric bell and controls. My Cree LEDs are sourced from Cutter Electronics in Victoria. The battery that I'm using is made by Envision and nominally 11.1 volts and 2.2 amp hours. It was purchased from RC Hobbies in Lidcombe. This size gives more than 4 hours operation in adaptive mode and 12 hours in low power mode. Here is a microcontroller board that I laid out with Protel, now Altium, and the blank boards were made for me by BEC Manufacturing in Queensland. The 3D printed ABS housing was made for me by Polygon 3D Printing in Victoria. Once connected to the battery, the controller never really turns off and only consumes 20 microamps while in sleep mode, which is less than the self-discharge of the battery. Pressing the button quickly while in sleep mode will flash the headlamp at full power, allowing you to warn others. Pressing the button for a few seconds will cause the controller to enter adaptive mode as indicated by the console LED glowing green. Adaptive mode controls the headlamp and flashes the tail light. In adaptive mode, the headlamp brightness is controlled by the bike computer's wheel sensor. So up to 42 kilometers an hour, the faster you go, the brighter it gets. On some unlit paths, it can be helpful to see not only what's way off in the distance, but also what's lurking just off to the side of the path. Here, the central lens has a narrow beam and the outboard lenses have elliptical beams. The gear indicators are illuminated by plastic optical fibres that tap off a little light from the headlamp lenses. A quick press of the button while in adaptive mode will force it to go to low power mode as indicated by the red LED, and it's useful for not blinding pedestrians that may be encountered on shared paths. In low power mode, the headlamp is still quite bright in daylight, great for being visible on long daytime rides. A slightly longer press will force the headlight into full power mode, as indicated by the blue LED, which can be handy on a rainy night on dark roads. Pushing the button for more than 3 seconds sends a controller to sleep and turns the lighting off. However, if you forget to turn the lighting off, it's not a problem because the controller will auto power off if there's no wheel sensor activity for more than 4.5 minutes. Before leaving the console, I'll talk about the mirrors. The one on the right is ultra wide angle. The field of view has about a 10-degree overlap with my peripheral vision, so I have full 360-degree coverage with that mirror and it helps when riding in groups. The mirror on the left side is less wide angle, which is handy for seeing objects more than 20 metres away and so is more useful when mixing with high-speed traffic. The mirror design was inspired by the Zefal bar-in mounting mirror. The trouble with bar-in mirrors is that they are the first thing to break when the bike inevitably falls over. This is typical of a donor mirror that I cut down to make my own designs. This is an ABS version of the mirror housing. The actual mirrors, the black nylon clevis and the hard rubber bodies, were made for me by Zelta 3D in Singapore. Unlike the ABS versions, the Zelta 3D parts have a nice finish to the point of being commercial grade. The final component is the tailbox. The shell, top, bottom and side panels are made from tough aramid fibre cloth, otherwise known as Kevlar. There are 2 shell stiffeners with balsa cores on each side that run fore and aft in regions that are unavoidably flat. The structural load carrier is made from carbon fibre. The tailbox slides onto the frame and is secured by a bungee cord. The bungee cord is just there. As you can see, the tailbox is quite spacious and it can hold quite long objects and has a capacity to hold 3 bags of shopping. Here is a structural load carrier. The tailbox carries loads fore and aft of the load carrier attachment point, which means that most of the weight hangs off the frame, more so than cantilevering, a significant reduction of stress. This is the drinking system, which is made from a camelback rip-off. The lid is secured with a kitchen cupboard push-push door latch. For my entertainment, there is a cut-down J-Car cardboard radio. The advantage of this design is that controls can be mounted remotely and I can operate them without having to stop. On the other side is a 4-ohm speaker. Between the seat and the shell is a foam filler. To remove the tailbox, just undo the bungee cord, unplug two connectors and slide it off the frame. The black plastic box contains the 5-volt regulator for the radio and the current control for the LED tail lamp, which is here. There are two banks of 4 LEDs inside a red acrylic lens that I moulded myself. The white reflective tape covers the overlapping glue seams of the shell panels. This method of construction allows the shell panels to be adjusted and then glued together to make a snug fit around my body. It feels more like you're slipping into the bike as opposed to getting onto it. Thanks for watching.